Good evening, everybody. Welcome to episode 1 in the budget build for a CNC router. I've got a bunch of things that I'm going to be working on that requires this machine, and I thought what better way to demonstrate learning on the fly than to do a session on Fusion 360, and we're going to figure stuff out as we go along. So I've got a bit of an itinerary of things that I would like to get through, and before I get in there, big shout out to CE Waffles, Silent Mode, and Alex Wavley. Thank you so much for hanging out. Appreciate you guys. As I said at the top of the stream, feel free to have a chat amongst yourselves. If you want to grab my attention, if I'm in the middle of something, feel free to do @IQ Workshop in the chat message. Tag me and ask you a question, and we'll get right down to it. Silent Mode, I'm doing okay. I'm doing okay. So let's do a bit of an introduction to what's going on here. So I am in the middle of a project for my son, and that is to build him a jazz bass guitar from scratch. That's partially been completed. Some of the test articles I have been working on to make sure that the CNC routing paths and all of those good things are working. And we've come across some challenges that we've fixed along the way, and we're now in the process of fixing one of the challenges. Let me just show you where we're at with the project itself. Here is the jazz bass that I've worked on so far. The body itself I'm pretty happy with. The pocket for the neck is really tight, really good. The fit and finish of everything on the body is great. The problem I have is with the neck, and specifically the length of the neck. What time is it here? It's 8 p.m. UK time. So this is a Fender style jazz bass, and you can see at the top of the neck in the headstock there's a bit of a defect. So let me grab the neck here, which is literally by the side of me, and I can demonstrate what the issues are with this. So let me just go on to the next image on my slideshow. Shot, welcome in. How you doing? Hope everything's good with you. So this is the workshop, and you can see just by here, right there, is my current CNC machine. Which was donated to me in a non-functioning state, and I've restored it. In fact, all of the machines, bar one that you can see in this image, are donated and were in a non-working state. So that's one of the things that we do here on the channel, is restore broken machinery. So we've got a lathe, wood lathe over here on the right. We've got a laser cutter, black and red laser cutter. 40 watt CO2. We've got the CNC here, which is just behind my video panel here, and then we've got 2 glow forges. That's something that's going to be up and coming on the channel. I got some restoration work or conversion work to do on a glow forge. There was a big fire in the bottom one, and the top one has been completely stripped apart. So I'm going to cannibalize 2 units, and hopefully, with a bit of modification, get a working one. So here's where we're at with the neck. So the neck itself is about 700 millimeters or so, from tip of the headstock to the bottom of the socket. In fact, it's 840 millimeters end to end. And that CNC machine is a 60/40, so it's got a working area slightly under 600 millimeters by 400 millimeters. So this neck does not fit on that machine. And I've machined this with it on a 45-degree angle, which meant there was a bunch of operations that needed to be done in order to knock out this neck. And for a first effort in pine, it's not bad at all. I've simulated putting the fingerboard on, cutting the truss rod pocket. I've machined everything. And there are 3 issues that I've got here. So the first issue I've got is this slot here was cut. That was a complete and utter mistake on my part in terms of operating my G-code. So that's human error. I guess they were all human error, right? The machine only does what it's told to. Then we've got an issue with the transition between the fretboard, or the nut area, down into the flat of the headstock. There's a difference in the height of the material. And if you flip this over, we get a similar issue here in the transition of the back of the neck into the back of the headstock. So the reason that these issues are here is because of the complexities of machining this neck. So to give an example, this neck is clamped down to the bed of the CNC machine with 4 locating pins. And those 4 locating pins are aligned around the center line of this neck. So the top side is then machined with the headstock hanging over the end of the machine. So once that's done, I milled the truss rod pocket, I glued on the fake fingerboard, and I did the machining of all of this bit here, right? Then I lifted this up off the CNC machine, flipped it around, and then machined the headstock, because now the headstock is available on the bed of the machine to have tooling on it. And that caused this issue just here. This was then picked up, rotated, clamped back down or across its center line, and the back end of the neck was machined and then cut and then flipped around. So there's like 4 times that this is either picked up and rotated or flipped end to end. So all of that movement means that the neck has to be clamped back in position perfectly in order to get a consistent result. Well, if you know anything about me, part of the reason that I got into digital fabrication is that I am absolutely horrific when it comes to hand tools, right? And my quality of finish isn't as good as it could be. If I took time to practice and hone the skill, then I would probably be a bit better at that. But that's not where my interests lie. My interests lie in tearing machines apart, figuring out how they work, put them back together, and then make them a usable condition. So what we're going to be doing is we're going to be designing a CNC machine that can machine one side of the neck in one pass before flipping it over and completing the same thing on the back side. So hopefully by the end of this live stream series, we will have a design that we can then look at customizing to my workshop and being able to build it out, and that'll be another set of live streams in the future. Gary T, welcome in. I hope you're doing well. Thank you for checking out the live stream. Appreciate you. Okay, just checking out a few messages here, being very popular. All right, let's go a little bit on the quiet side, shall we? Just do that. Awesome. So, yes. So we're going to build in. We're going to build in some the ability. We're going to build in some of the ability to customize the machine. So, for example, if we have a component that is slightly different, we'll be able to come into our CAD tool, and we're going to be able to make some changes in some of the variables that you can set up, custom variables, and the machine will automatically resize itself. And we'll need to do that prior to ordering any of the cut components. So yeah, let's get into the, so that's the project overview. So to put it succinctly, we're designing a CNC machine that can cut and machine a neck for a Fender jazz bass style bass guitar. And we're going to be using free access tools to complete this work, end to end, including the electronics that's going to drive this thing, the software, everything that's going into this is going to be free tools. So I'm not dumping just a lot of cash into this and just making this project a purchase, a kit. This is something we're designing to our specifications. So going back to some of the design constraints. So there are some design constraints that we have to consider. The first of which is going to be the drive mechanism. The drive mechanism is going to be using off-the-shelf parts for the ball screw. We're going to use ball screws to drive this as opposed to GT2 belt or any sort of timing belt. And the reason for that is that the ball screw can give us an improvement in torque that the motors can give off. We're going to be able to have precision control where a belt may stretch over like nearly a meter. That could be a couple of millimeters worth of inconsistency or error. So we want this machine to be as accurate as we can make it. And the way that I know how to do that is to use ball screws. And the reason that the ball screws is important, like belt machines are great, not to say they're not, but ball screws are going to give us that oomph when we decide to plow a bit into hardwood, or if we're going to go into aluminium later in future projects. We want to be comfortable that the powertrain of this machine is going to be up to the job. So that's the first constraint. The second constraint is space. The space of the bed, so we have to have enough room to be able to machine this neck. And we also need to consider the space constraint on the bench. So where all those scraps of wood in between the CNC machine, which is just there, and the bandsaw and the screens, there's two pillars either side this window. So we've got the width of the bench and we've got the width between these two pillars as an absolute maximum. But we're not going to worry too much about that right now. We're going to get into the design of things, and then we can play with the variables a little bit later so that we can make it fit our requirements. Ball screws are excellent but can be expensive. Indeed they can be. So we're going to use global suppliers in order to try and keep the costs of this machine build down. A machine of this type probably going to cost you off the shelf in the region of $2,000 to $3,000. So my target to build this machine is going to be somewhere in the region of $500 to $1,000. That's what I want it to be. We're going to find out how close to this guesstimate I actually am, and we will see where I can save money by cannibalizing other machines for parts, and we'll see what we can do. All right, so let's get into the Fusion 360 setup. Let's look at how we're going to set up for business inside of Fusion 360. And for clarity, I am using the personal license of Fusion 360. So that's freely available. I have a video that talks about how you can get Fusion 360 for free. There are 3 different licenses for Fusion 360. There's the personal license, which is totally free but with restrictions. The educational license, which is free but you have to qualify being in an educational institute. And then there's the full paid license. I've not yet come across any sort of constraints in the personal license that inhibits me as a maker. That's not to say that hasn't inconvenienced me, because you can only have a maximum of 10 files open in a read-write format in the whole platform, right? So you can turn files off, make them read-only. So yeah, it can be a bit of a challenge, but let me just quickly show you how I get around that. So here's Fusion 360. Let's get away from our task list and have a nice clean window. So here is the navigation panel, and this shows us where all of our files are. And there's a couple of ways that you can play with the open files to get around this 10 file maximum, right? So bearing in mind, editable files is the key phrase here. What you can do is you can do one of 2 things. You can either, 1, design a component, and once it's complete, mark it into a read-only state. Then create a separate assembly file and bring each component into your assembly file and use joints to assemble the overall thing that you're trying to make. The other thing that you can do is to create components within Fusion 360. And that's the route that we're going to go down, because I'd like to have everything combined. And we're going to have the ability to change some variables so that the machine can change shape, change dimensions on the fly. And to do that in individual component files would be a bit of a pain. So yeah, you'll see here at the top, it says I've got 6 of 10 files open. If I click this editable option and change it to read only and just say yes, this will now change to 5. So I've done 0.9x FreeCAD. So I'm not a big fan of FreeCAD's user interface. I love the fact that FreeCAD is free, it's open source, and it's like a fully fledged CAD application for anybody and everybody to use, right? It makes it completely accessible as long as your PC runs it, you know, which is pretty difficult not to be able to run it. From what I can see in terms of specs, then, you know, it's a great application. Unfortunately for me, the user interface is counterintuitive to the way that I think. So I will more than happily, like suggest other applications to users. I showcase other applications like Alibri, like FreeCAD. What else have I done? I've done a top 5 free CAD applications. If you look in my lists, video list, you'll find a couple of videos about that topic. So it's all about what works for you. Fusion 360 works for me. That's interesting. I don't know whether or not the parametric variables carry across to different files. I don't know if they're embedded in the file itself. I think they are, as opposed to in the application. We'll have a look when we get in there. Yeah, I'll give it a look. I'll give it a look. I mean, if it's something that is going to work in my workflow, then I'll absolutely give it a shot. So the one reason that I went down the Fusion 360 route is because that it drives all of the workflows that I wanted to get involved in at the time of starting my maker journey. way back in 2015. So we're approaching 10 years of my journey right now. And I started with 3D printing. I scratch built my first 3D printer, and Fusion 360 helped me all the way. I then took in Big Red, the laser cutter you saw in the workshop downstairs. Recovered him, and I was able to do, laser cutting with DXF files. And now I'm using it for CNC G-code processing. So I'm really happy with Fusion 360. But if it's not your flavor of CAD, that's fine. There's room for everybody. A lot of the principles that we're going to be covering are, transferable, I would imagine. There'll be an equivalent way of doing things. Alrighty, so I've got a test job that I live stream over on Twitch. Just having a play around just to see how I was going to figure out how to do things. And we're not going to do what we did in this test job. If you have a look at this test job, so this is me modeling the ball screw itself. And while this looks a really cool ball screw, one of the problems is how complicated the timeline is in order to get this model. There's 17 different operations, I believe, in getting this ball screw. And I think after sitting down and just giving it a bit of thought, I think I can be a bit more efficient. So we're hoping to finish the actuator, the Y-axis actuator, in this live stream. So I think we need to make a start, otherwise the time's going to get away from us. So let's just quickly check our list. So let's get into the Y carriage design. And then let us crack right on. So what we're looking at here is the user interface for Fusion 360, and we have a hierarchy tree starting with the root of your design. Now, if you're modeling a single object, most people will just start designing in the root. But because we're going to be creating an assembly, I know ahead of time that I'm going to need components to join to other components. So we're going to join things up a little bit later on. So in which case, I'm going to start out by creating the component for the Y-axis actuators. So here's a good question. Load a ball screw from the McMaster Car plugin. So if you're unfamiliar, you can import McMaster Car parts into this into Fusion 360, and that saves you a ton of time when you're using off-the-shelf parts. That is an excellent suggestion, and we will be doing that for some of the components, but we will not be doing it for the ball screw. The reason for that is I don't currently know where I'm getting the ball screw from. So I'm going to set up the ball screw with a set of parameters there's geometric or geometry landmarks that all ball screws have, right? So what we're going to do is we're going to paint that, we're going to design those landmarks, and then we're going to tie those landmarks into a variable system so that we can change them on the fly. So if I buy a ball screw from another manufacturer from the one that we're going to look at today with different dimensions, all I have to do is to pipe those dimensions into Fusion 360, and I can see in the computer if I've got a problem with the components ahead of time. So like I say, what we'll do is we'll figure out what our design is going to be. Once we know the design is good, we will order the ball screws, the linear rails, the linear bearings, and once we have those in hand, that sets us that sets a physical landmark that we can then move on into the design, and I can get everything tested. Once it's tested, I can get the aluminium extrusions cut, And then it's pretty much a case of assembly for the motion system. Then we get on to the electronics. So we're breaking this project down. There's the mechanics and motion system, there's the electronics to drive the mechanics, and then there's a software to drive the electronics. So yeah, there's much fun to be had. Right, so let's go ahead and create a new component. And we'll call this component y-axis. Y-axis actuator. All right. So the next thing that we're going to do is we're going to create another component in here, because this is a sub-assembly. And we're going to, let's unground from the parent. Let's right click, let's go to new component, and we'll call this, we're going to do this ball screw. So what we're doing is we're setting up a hierarchy for our y-axis actuator. So as I mentioned here in the test job, I did all these operations down here to get this ball screw. And that's not particularly efficient. I think I'd like to have a lot fewer operations, and I think I can do it. I think I'm going to do it. We're going to try, at least. So I'm going to be alt-tabbing between a browser window that has a technical drawing of the ball screw and Fusion 360. It's always good to have some reference material that you can work to and from. And that's where we're going to go. So let's have a look. So here is the technical drawing of the ball screw. And we've got some dimensions associated with this. The only one that we need to select is L. L is not currently known. So let's get on and design this ball screw. All right, so first things we're going to do is start with a sketch. And I'm going to put the sketch on the bottom plane. And the first thing I'm going to do is add a construction line. And I do that by tapping X on the keyboard to go into construction line mode, or you can use in the sketch palette, you can change to construction. And then L, and I'm going to put a right angle line just coming out the side of my drawing, just like that. And I'm going to use this as a grounded reference point. Okay. So we already know that we're going to have a bunch of variables. So let's start building our variable setup. So if we go change parameters in the modify panel, and we're going to create a new parameter, and we'll call this y ball s y ball screw length. I'm trying to abbreviate it to keep the name short, but it's up to you how you choose to label your variables. And I'm going to put in an arbitrary value of 700, right? Okay. So I'm going to draw a line on this green center line here. Oh, we're in construction mode, so let's turn that off. I'm going to put that there. And then I'm going to put one down the bottom. Okay, so I'm now going to dimension from this center line to the top. And the cool thing about Fusion is you can put formulas into your dimension values. So Y ball screw length. If I do that, that's going to be the overall length. So I want it half of that. So all I need to do is to put a /2, divide by 2, hit return. We've now got an end of our ball screw, which is the correct length from the center line. So I'm going to do exactly the same for this line down here. All right. And now I'm going to connect the two ends of these lines down the center line as a solid line. And it'll become clear as to why I did that. So let's go back to our reference. Okay, so we can see the end diameter of the ball screw is 8 millimeters on both ends. So let's create a new variable and we'll call this YBS core diameter. Oh, helps if you create a parameter. There we go. And we're going to say it is 8 millimeters. Okay. And then all we do is dimension that. And because we're actually measuring half of the profile, we're going to divide this number by 2. We're going to use an operation to effectively create the cylindrical ball screw from this sketch. 8 millimeters diameter divided by 2. Perfect. Awesome. All right. So now we have a section which is a 10. Right, so this section here is now 10 millimeters. As is this section here. So let's call this, let's create a new variable. And if anyone has any questions as we're going along, feel free to ask away. YBS core 1 diameter. And this is 10 millimeters. Okay. So what we're going to do now is I'm going to draw a line. Now, which I've got to think about this. Okay, let's be careful. Let's be careful, right? Let's do it from the bottom. We've got a piece of shaft, it comes out and it then moves up. And it moves in, and it comes up. And then we get this little indent. See, this is like really horrible, right? This looks absolutely horrific, but trust me, it will work. It will work. Okay. So the first thing I want to do is I want to figure out where is it? Where did I put it? There is a section here. There it is. I want to figure out where this little slot sits. So this slot sits on the end first and foremost, it is 0. Right, so the back edge is 7 millimeters from the end of the bar. Okay, so this is for a circlip. Okay, so let's add a new variable, and this is y bs circlip distance. Okay, and it was 7 millimeters. So the first thing I'm going to do is just dimension between these two, and we will come back and we'll actually set a variable for that also. So this is this is the slow part, right? Because we're building and layering our variables, and once that's done, we'll be able to drive this ball screw through changing the variables, and it'll look like magic, right? This will pay off a lot a little bit further on down the line. So we're now going to dimension between here you see I made an absolute pig's ear of this, but it'll work. And this was the y circlip distance, 7 millimeters. Go. Boom. There we go. So we now got our circlip in position. So there's a couple of things that we need to figure out. Is the distance between here for the circlip and the depth of this cut. Now, do you know what? I'm probably not going to go down the road of getting that 100% perfect, because typically what's going to happen is the circlip is going to come with the kit. I just need to know its positioning, where the slot is, so I can put the circlip on. As long as the slot, the back edge of the slot is in the right place, everything else is a little bit flexible in that regard. So let's dimension that from there to there, and we'll make that 1 millimeter. Oh, did you see what happened there? This actually reduced in height. So I now need to fix that. So dimension there to there. Dimension between these 2 points. Okay, so this is diameter divided by 2, and that's it. We're locked back in. Awesome. Alrighty. So now I need to know where this shoulder comes in. So this shoulder comes in 10 millimeters. So new variable. And we'll call this Y ball screw. What do we call it? Top shoulder. And that was 10 millimeters. Okay. So now if I dimension, check where those dimensions are from the end of the ball screw to the shoulder of the of this section. All right. So we'll dimension that. This looks so unimpressive right now. But the payoff is coming. Okay, so this was top shoulder. Okay. There you go. That'll make it a little bit more understandable. Be very careful about your naming conventions of your variables, because if you start having lots of different variables with cryptic names, it's going to be very challenging to try and figure out what it is you're doing, right? So don't trip yourself up. That is a pitfall if you are not careful. Hey, Web Monkey, welcome in. Hope you're doing well. Okay, so that's this end of the ball screw completed. Let's have a look at the other end of the ball screw. All right, so we've got this shoulder to sort out, and that's pretty much it for this. We're blocking this out, right? We're just blocking this out. So when I say blocking out, I don't know if any of you are familiar with the animation term of blocking, where you use like very large geometric shapes to represent a character and where it is in a scene. And it's a very crude way of like saying where the character is. This blocking is very crude in that we're doing here in Fusion, and we're going to refine it until we have a nice, what appears to be engineered ball screw, right? So let's select this. We're going to create a new parameter. I'm going to copy this, save my typing, paste it in here, and I'm going to change it to B shoulder, bottom shoulder. And what was the value here? So eight millimeters, 10 millimeters. Okay, I'm going to just put an arbitrary 55 in there for a minute. That is arbitrary, because I just realized we've got a problem here. Got a problem in that this line doesn't, it's not where we want it, right? We got more going on here. It steps like that. Let's trim that off. There we go. That makes a little bit more sense for what we're doing. So let's get this length here. Oh, Control Z. Didn't want to trim that. Okay. And this is bottom shoulder length. I think we'll have another variable in there. That's a diameter. This is a diameter. Bottom shoulder length. I'm just going to put an arbitrary 10 in there for a minute. It's actually 15. I'm going to change my parameters names in a minute, because I can see that I'm going to get myself mixedy muddled up if I'm not careful. Okay, so this is bottom shoulder length, 15 millimeters. Perfect. So the next thing we need to do is to get this shoulder's different distance. And I think we're gonna need to rework these variables. And as I said, this is a work along. I'm figuring things out as I go along. Some of these things I've done before, some of these things I haven't. So we're learning as we go. Right, okay. So what are we gonna call this? Shoulder 2 length. bottom shoulder to length. Okay, we'll call that bottom shoulder to diameter. And then let's go length. What was the length? 39. Okay. So let's do the diameter from here to here. Bottom shoulder to length, 39. Awesome. And then diameter here is 10 millimeters. No worries, Alex. Appreciate you hanging out, buddy. So this is 10 millimeters. So I put it as 55. We're going to see the power of parametric, right? So there's 55, but it's not 55. It is 10 millimeters. So we want to change, in fact, divided by 2. There we go. Modify, change parameters. This was 10 millimeters, I believe. And now we click OK, and we're now snapped into position. Now, one of the things I'm noticing is that my lines are not turning black. One of the things in Fusion 360 is when your lines become fully constrained, they turn black. And for some reason, these lines are... okay, I see what's going on here. Can I fix this? Okay, fixing it doesn't do anything. Doesn't do what I want it to. So I think what I'm going to do is I'm going to constrain that in a second, and this should all turn black shortly. Can I set a midpoint? Awesome. Okay, so that line's now turned black. There we go. So I've grounded that line. These are all starting to snap into position now. Okay. And then we'll say new variable, y-axis, ball screw diameter, and I know this to be 12 millimeters. And okay. Now you can see I'm doing some math in some of these variables. Why am I not putting that math into the formulas? Well, the reason for that is because I want the formula in the drawing and not the variable, because the variable may be used elsewhere and that has an absolute value. And I know then that I'm not doing something silly, right? All right, so here we go. We want to dimension this section here And this is YBS diameter 12 mil divided by 2. There we go. And this, believe it or not, I finished the sketch. This is our ball screw. Doesn't look like it at the moment, but we're going to use a little trick in Fusion 360 to give us our ball screw. And that is when we go into the create section, we're going to use a revolve option. Where's our revolve option? There we go. And our geometry automatically selects because it's the only geometry in the drawing. And now we have to tell it which axes we want to revolve around. So I'm going to choose the center line that I put in here, like so. And then we have, if I click on OK, we have a very crude ball screw. We've got a couple of operations. We've got 3 operations that we need to do now in order to get this just so. And the first operations I'm going to do is I'm going to put a chamfer on these edges. Just playing with the value. Going to put a 1 millimeter chamfer on there. Nice, nice, nice. And now let's add chamfer here and here. Okay. So now with 3 operations, we're now starting to look like we have a ball screw. Okay, so let's go back here. So we've got a 16 millimeter section of M10 by 1 threads. So let's put a thread on this section of the bar. So we select it. We create a thread. M10 by 1. We want it modeled. Okay, so we're coming across an error. I don't know if you guys saw that error. Let's bring that error up. An existing fillet or chamfer could not be deleted. Try suppressing or deleting the existing fillet chamfers before attempting the operation. So what Fusion is telling us is it can't apply the thread to the part because we put the chamfer just here, right? It does not like that. So here's what we're going to do. We're going to roll this marker back in the timeline by 1, and that'll just hide the chamfer. So it should allow us now to create the thread on this bar. M10 by 1. We don't want it to be the full length. We want it to be modeled. And we want it to be, is it 16 millimeters? 16 millimeters. So I'm gonna type that in. I think I'm all variabled out right now. Okay, 16 millimeters. In fact, we are gonna put that as a variable because that attitude is gonna bite me in the bum. I can tell. Right. Okay. So Y ball screw thread length 16, go. All right, and now let's just edit this. And what we'll do is that 16 millimeters that we typed in here, what we're going to do is we're going to change that to Y ball screw, where is it, thread length, there we go. And then we click on OK, and we don't see a change because, you know, we didn't adjust anything. All right, so It's telling us that it's not happy about applying chamfers, so I know why. So I want to get rid of that edge. There we go. There we go. One more operation. One more operation, and we've got our ball screw. Okay, and that is going to be figuring out how to put the ball screw geometry. Do we need to do this? We probably don't, but I'm going to just to demonstrate how you would do this. So we're going to use, let me see, coil. We're going to use the coil feature. And we're going to put the coil on the end of the bar, like so. And we're going to make it 12 millimeters. In fact, no, we're not. We're going to make it Y ball screw diameter. There you go. So we've got a variable that's driving that. Okay. We now want okay, the section size. I'm going to change the section size to 1.5 millimeters. And we're going to say negative Y ball screw length. And then we're going to okay, that didn't like that. Why? What's going wrong? What's going wrong? Let's go 20. Ah, 12. I see what I did wrong here. Section size. What is the variable that's changing? Okay, so that should be 1.5 millimeters. There we go. There we go. I'm working out which, the height. It's the height. Okay, so negative Y ball screw length, which will be, where are you? There you go. Bosh. And now we've got to bump up the number of revolutions. So let's say Y ball screw length divided by 3. Okay, I understand what that's doing. It wants a number. It wants a number. So let's just say 200. Okay, Fusion's having a think now. It's got to calculate this out. Okay, I'm going to click on OK. I want to see what this has done to our model. And it's done a pretty nice job of making a ball screw. Okay, we're going to put in a new parameter. Y ball screw turns. The value is 200. Now we don't want any units here. This is a no units variable. If you put a units variable in there, it's gonna not be happy, right? So we click on OK. Let's go right click, edit this feature. Okay, where it says 200, We're going to go Y, ball screw turns. And then we're going to say OK. And we now have a means to drive all of this. So let's, for argument's sake, say that we've just decided we're not actually modeling the y-axis. We're going to model the z-axis. The z-axis is much shorter. So the overall length of the z-axis, let's say it's 200 millimeters. What we can do, because we have this now built in a parametric way, we can modify the parameters. So in here, instead of 700, if I just shrink this over so you guys can see what's happening to the model as I change the numbers. Let's say it's going to be 200 millimeters, right? As soon as I tab out of this, it calculates the ball screw. Right? Now it's complaining about the ball screw's number of turns. Okay, so let's change the number of turns from 200 to 75. In fact, let's change them to 25. And you can see the model is now changing. If we said that the shoulder here is actually 50 millimeters, it changes it, right? So we now can drive this model oh, it's having to think. Was it 39? Yes, 39, 1539. Okay, so let's put this back to an arbitrary 700. And let's go back to 250. Let's go 250. Okay, so we have a ball screw. I'm pretty pleased with that. Does anybody have any questions about how we made this ball screw? We're gonna do a comparison, right? I'm gonna save this now. So this ball screw has got 1, 2, 3, 4, 5 operations. There's 5 operations to get this ball screw here versus the test job that I did, which looks the same, right? It has the same sort of parameters based. There's variables in here that drive all of this, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 different operations in here to make this ball screw versus 5. And that, I would say, is the key to Fusion 360. How can you achieve things with the fewest items on your timeline? And the reason why that's important is that the deeper you go into your designs, the more complicated the designs become. The chances of you getting yellow icons appearing on your timeline as a warning. Warning is saying, Fusion's seen you did something, or something's disappeared. I can kind of work it out, but you really should know this has happened because it might get worse. Red icons on your timeline are an indication that something is broken. Your design is not working the way you intended it to. So the fewer operations that you put into a design to get the result, the better it's going to be for processing power. It doesn't have to think so much about stuff. It's more efficient. That's the right wording. It's more efficient. So here we go. We have now got our ball screw. we now need the component that makes up the frame of the linear actuator. And I've got some, I have got a website that I'll be ordering my parts from. Let me bring that site up. Where are you? Where are you? You are hiding. Okay, so this is a company in the UK called Ooze Nest, and they produce, they do various different machines. There's a CNC machine in here for about, I think it's about between 16 and 1900 pounds UK, right? So you'd probably be looking at somewhere in the region of about $2,000. So they also sell the extrusions. Now, as you can see, this is a C-beam extrusion. It's quite a complicated bit of geometry, and to try and model this would be such a pain. I would hate it, right? So one thing that these guys do is, if you scroll down to this technical section, you've got the description of the product, what it's made from, the quality of the aluminium or aluminum, depending on where you live. You know, it's a data sheet almost. And it gives you some details about the specifications. Now, if I scroll down to here, I've got a 3D model download or a drawing download, which is awesome, right? A drawing download would be the best, but it comes down as a PDF. So that's not what I need. I choose the 3D model download, and I have imported it into Fusion 360. And this is the C-beam. Now, the model itself comes in just like this. Now, I could potentially just bring this into my model and use it as is, but it's the wrong length and I can't control it. Let me show you its length. So I use the eye to inspect, choose the one edge, flip over, choose the other edge, and Fusion 360 tells me that's 500 millimeters. So that's less than ideal for me. So what I'm going to do, I'm going to make this as easy for myself in the future by giving myself a little bit of hardship now. Like we did with the variables in the ball screw design, I'm going to take a trace of this profile and we're going to bring that into Fusion. So here's how we do that. So the first thing we do is going to create a sketch, and we're going to place a sketch on the surface of the extrusion itself, like so. Now, because I selected that, it's already traced it. I can click Finish Sketch, and then I can go into my sketches, right-click, Save as DXF. And I'm going to call this C-beam. Okay. And I'm going to go and put this into my editing drive. And we'll put it there, C-beam. Save. Right. Now, this is read-only at the moment, so I literally just took a trace of the extrusion. It is pretty nice, silent mode. It's pretty nice when you can get some components in your designs, and I'm going to show you an awesome one in a second. Absolutely love this one. Right. So let's go back. I can close this. It's going to ask me, do I want to save? I'm going to say no. I'm going to create a new component in the actuator. New component, and I'm going to call this C-beam. C_beam. Okay. So you'll notice this has now gone grey. And the reason for that is that this component has just become active. If I select this one, it comes back solid gray again. So be careful. You'll notice my timeline has now gone to 0. Right? Timeline's now gone to 0 because we're in a new component. So let's right click, let's unground it. Awesome. And I'm going to hide the ball screw because I don't really need to see it because we're going to join all of these things up in a moment. So here we go. We're going to insert a DXF and we're going to insert it on this plane here. I now need to navigate to the file on my computer and choose the C-beam DXF file. And there we have, at the center of the drawing, the beam. Okay. And there it is. So what I can do with this now is I can extrude my beam as long as I want it. So let's go ahead and do that. So I'm going to select the geometry of the extrusion. I'm going to tell it that I want it symmetrical and that the measurement that I want to put in is the whole length. And I'm going to marry up with the ball screw length. Okay, it's probably not going to be the right size, but I'm not overly worried by that at this moment in time. Would help if I spelled length properly. I just noticed I spelled it wrong. So anyway, so there is my beam. Now if I bring in ball screw and I go back to the root of my design, you can now see that the ball screw is kind of like embedded. It's embedded in the extrusion, but that's no biggie. That's no biggie. We'll get that sorted out now. All right. So I guess if I hide the ball screw and I hide the beam, the next thing I need to do, if I jump over to my supply. So there's a nut and there's some brackets that come along with this, and I'm hoping that we've got some design data on the bracket. And we don't. That's interesting. So we may, okay, we're going to abandon using that bracket. Oh my gosh. So the bracket and the block. There's a couple of things in here we don't know anything about. So, if you recall, we said that the trying to think of my words here. We're going to make our own block. So what I'm going to do is I'm going to create a new component. I'm going to call this ball screw end block. Okay, ball screw end block. So I'm going to insert the DXF file that we just used. and I'm going to create my own. I'm going to create my own bracket, right? So let's see how we can do that. So we got a couple of reference points. So I'm going to draw a line. Would help if I just get into this sketch, right? Edit the sketch. I'm going to draw a line from here. I'm going to draw it out beyond here. Over, and I'm going to do a really horrible job, right? I'm going to do an absolutely terrible job. Okay, and I'm just going to fix this up with a couple of design constraints. All right. So we said that the internal diameter was 8 millimeters. I got, where is core diameter? And I'm going to give it plus 0.5 millimeters of tolerance. Now I'm not accounting for a bearing here. There needs to be a bearing in here, but that at this point doesn't really matter too much. And I am going to trim. Okay, will it allow me to trim? I'm going to get rid of a lot of geometry here. Because it is not needed. Okay, just clean this up a little bit. Okay, I just realized I deleted something I wanted. Bugger. Okay, I can get it back though. Okay, I'm keeping 4 holes because I want a mounting option. Okay, again, if anybody's got any questions about what I'm doing, why I'm doing it this particular way, just yell out in chat and I will more than happily highlight your comments and we'll get into your questions. Other than that, I'm just going to keep working away and try to signpost all the things that I'm doing. Okay, we're going to keep that. All right, I'm going to fix some of the stuff I broke a second ago. All right. Let's get that bit I broke back. And we're going to create a mirror. I'm going to choose the bit that I want to mirror and where we're going to mirror it to. We click on OK. I've now got my drawing back. I can get rid of that, and they stand alone by itself. Okay, so this is just a mock-up block, right? This is all I want to do. We're going to finish the sketch, and then we're going to extrude this component by, I don't know, let's say 10 millimeters. So it's got some substance to it. And then we're just going to round off the corners. Just because I don't like things with sharp edges to catch my hands on. I'm probably not even going to use this part, right? This is just for alignment purposes. But then again, once we've got it aligned, we're probably going to like fit it. So let's start putting things together, right? So let's select the actuator as a component, and let's bring in the C-beam. And what we're going to do is we're going to mount this bracket onto the C-beam, and we do that by pressing J on the keyboard for a joint, and we're going to select this face, and then I'm going to select the hole. And now I'm going to select the corresponding hole that it's going to mount to, like that. And the component just slides over into position, right? Then what I'm going to do is, because I need an actuator either side, sorry, I need a cap either side, I'm going to create a mirror. Where are you? Where are you? Where's the mirror? Mirror, mirror on the wall. Okay, we're going to select that object, and then we're going to select the mirror plane. Now, because of the way I've done everything, and the center of all of the models, the center of the models is at the center of the origin of the whole design. I can just use the origin as a plane to mirror things, and I create a capped end, right? Pretty cool, huh? I think so. And we got a warning though. What's the warning? Compute failed. I beg to differ. I beg to differ. Okay, let's try that again then. Mirror. Okay, that's going to be the origin. Want to use this origin, right? Origin of the actuator, not the origin of the overall drawing. Okay, now it's happy. I think I used the origin of the overall drawing, so it would be a global origin as opposed to an isolated origin. If we then take this actuator and mount it somewhere else and change its orientation to the global has changed, but the orientation to itself has not. That's why it was complaining. All right, now we can get the ball screw into play. Let's hide the C-beam and the end block. And what we're going to do is we're going to assemble it with a joint, use the tip, bring the block in. It flipped it. Don't want it flipped. Then we click on OK. Let's bring in everything now. We now got a ball screw, which, to be fair, get this into shot properly. There you go. Let me turn the ball screw red, shall we? I'm going to apply a material to the ball screw. Oh, that's no. Unassign and delete. Get rid. Okay, let's just put an ABS plastic. Oh, there's a product update. It won't let me download a it wants me to close this. Oh, why? Okay, red. We got something red. Oh, all of these things are unavailable. Red paint. Okay. What do we got here? For some reason, it won't allow me. Okay, it wants to restart Fusion. Okay. So let's save the project before we do anything, and we're going to restart Fusion. It's not allowing me to. It's not allowing me to download these parts. So let's get and restart, shall we? We're saved? Yes, we're saved. Let's go ahead and restart Fusion. Great. Get an update live on stream. So the ball screw that I want is probably somewhere in the region of 700 millimeters long, 750, 650. How much is a 650 ball screw? It's 44 pounds. Nice. We're going to need 2 of those. That's going to be 88 pounds. Just for the ball screws. Hey. And that's the cool thing. I'll be able to price this machine up before I even like get somebody to cut anything. So, okay. How are we doing on the restart of Fusion? You're all set with the latest update. All right, let's see what we got. Now you'll notice that, well, you won't actually because you can't see very well. So let's get the appearance in here. Okay, make that white. We'll make the end caps black. And this could look horrible, right? Okay. So from AliExpress, they do quote the shipping prices. So it's £3. So you got the price just here for the part, and then it's £3.34 for the shipping, and it also gives you an indication of the delivery time. All right, so we can see from here, let's get rid of this panel here and just maximize this right out. We can see here that the bit, it sticks out a bit, right? It doesn't go all the way through. This C-beam is the wrong length. Well, the cool thing about this is we can go into our C-beam and we can go in here and we can say modify, and let's say change parameter. We're going to put a parameter for the, in fact, no, we're not going to change the parameter. We're going to modify, edit the feature. Okay, so I'm going to take 40 millimeters off. Okay, so we've taken 40 millimeters off. Let's go to, and now we can see we've got the ball screw hanging at the back here. So if I edit the joint, okay, and then we'll bring it this way by 40 millimeters. Or even 20 millimeters. Okay, we can't get the circlip on, but that's fine because we can change the thickness of this end cap. That's not a problem. So what we're figuring out here is where do we want this to be? So let's get a clear picture of where this ball screw is currently sitting and what can we do about its placement. So what we got to remember we haven't figured out is the nut. So this is the nut that goes up and down the ball screw. This is also a side view of the nut. And we also haven't considered the block that this nut goes into. Right? So we've got to figure that out as well. Otherwise, if we get that wrong, we're going to be stuck. So we've got to figure out what the interferences and clearances are for this actuator. So in order to get a decent view, we can go into the inspect menu just up here at the top, and we can use sectional analysis. And what we can do is we can cut away at the model and look inside to see where things are internally. So if you had like a shelled model and there was components inside with galleries, and say for example you're looking at an engine block and you wanted to see the galleries of where all the water goes, you can use this in cross-sectional analysis to cut through the model and see those galleries. So all we do is we select the plane and then we can just like slide the sectional analysis up, and let's go like 150 mil up the shaft here, and then we can just orientate ourselves and we can zoom in and we can kind of see, we can see where this is. So what I think we might be able to do is to lower this hole down by, I don't know, let's say a finger in the air amount, right? Let's go in and activate that block. Let's edit the sketch, and we're going to dimension it from the center of the drawing. It's currently at 20 millimeters. Let's go half that. Let's go 10 millimeters. Finish the sketch, and it's instantly updated. Right, so that's now sitting inside that C-beam, inside that C-channel. In a completely different place now. Is that position where we want it to be? I don't know. Maybe. Maybe not. Possibly, possibly not. But we've got it. We've got a means to be able to adjust it. Right, let's get rid of the sectional analysis because I'm not really interested in that right now. So that's gone. And you can see we made a change to this one, and because we used the mirror of it, it's It's now here, right? It updates it. I love working parametrically. Now we're going to need 2 y-axes, but we're only going to model 1. As you've seen, we've already used the mirror tool. So once we've made one, we'll position it in our design, and then we'll mirror it over to the other side because they're going to be identical. Alex earlier mentioned about loading things in from McMaster-Carr, right? This is what Alex said earlier. Load the ball screw from McMaster-Carr plugin. We won't be doing that for the ball screw because, as I said, we needed it to be custom. But what I will be doing is I'm going to bring in a stepper motor for the purposes of figuring out where our stepper motor is going to go. Now, in the machine that I've got downstairs in the shed, in the workshop, the stepper motor just bolts onto the end of this shaft and sticks out. And personally, I think that's pretty ugly. I think that is pretty inefficient in the way that it's put together. It's a waste of space. So what I'm thinking of doing is to fold the design. So I'll take the motor off, fold it 90 degrees so the shafts are parallel with each other, and then connect those 2 shafts with a pulley system. Now, I did say earlier about not using a pulley system, but this is a design decision that I'm making in order to make the machine a little bit nicer. Now, if this doesn't work and it goes horribly wrong, it's not going to be the end of the world. I can probably disconnect any mechanisms that I make and 3D print brackets and bolt the motor on in the traditional sense, right, and have it sticking out. But I don't want that in the design right now. I just want I want the bench space used for the work area. I want to get the maximum amount of work area that I can possibly get for the bench space that I've got. And having a motor taking up some of that space and causing the machine to either overhang the bench, which is, I don't want that. I think the only natural course to take is to fold that into the design. So I'm not going to model, you'll be glad to know, I'm not going to model a motor. I'm going to grab one from the McMaster-Carr plugin, and let's do that now, just so it's in the design and we can kind of play with it, mock it up and figure out, you know, what are we going to do with it. So to insert a McMaster-Carr component, we go into insert and there's an option, McMaster-Carr. And what this does is it opens up the McMaster-Carr website inside of Fusion 360, and we can actually start searching for components. And there's threaded rods, there's nuts, there's bolts. I have actually, in fact, I have actually downloaded a wing nut from McMaster-Carr and 3D printed it for a project. So there's, from a practical sense, there's plenty of things that you can do. And so the cool thing about this is, if you live in America or in Canada, you can order your parts directly from McMaster-Carr. So you can literally grab off-the-shelf parts, bring them into your design something custom to mount it, and blah, 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 blah. Then when you order that exact component from McMaster-Carr, you know it's going to work in your design. You do need to figure out tolerances, especially if anyone's done 3D printing. You'll know if you try to, model a hole that is exactly 8 millimeters in diameter, there is going to be a tolerance value that the machine can go down to. So just be mindful of that. And as long as you keep tolerances in mind, you won't have a problem. So we're going to go into the search. And we're going to search NEMA. And we're going to go for a NEMA 23 stepper motor. And then we get a bunch of options here, right? Let's see if I can maximize this window a little bit to give us a bit more of a view on what the options are. So we've got stepper motors, stepper gear motors, servo motors, positioning slides, electric actuators. There's a bunch of things, right? So we're going to go for a stepper motor. Now, we're not looking for the exact motor type. We're going by how can I put it? This a form factor. NEMA 23 is a form factor. So essentially, all NEMA 23s will be manufactured to a specific sort of faceplate design. And that's all I'm really interested in. I could go and buy a NEMA 23 from AliExpress, from RS, from wherever, McMaster Car even, right? It doesn't matter. A NEMA 23 mounting hole is a NEMA 23 mounting hole. They're all the same. So this is just a mock-up. The only thing that I really need to be careful of is the shaft length. The shaft length on my mock-up needs to be close to, if not bigger, than the shaft length of the motor that I'm going to be using in real life. As long as it's bigger, you know, longer, then I should be in good shape. Right, let's get this McMaster Car window a little bit bigger. It's been a little bit problematic to find the handles to drag it. Being really finicky. Right, okay. All right, so here we go. We got all the technical specifications of these NEMA 23s, right? So I want a square body NEMA 23. I don't want one with the linear actuator. There's some pretty cool stuff in here, to be fair. Wet locations. Economy stepper motor. That sounds like what I want. The only thing I'm worried about is I think it might come with the cable modeled. I don't want the cable. That's going to be a pain in the bum. I really don't care about the cable. That's got cable. That's got cable. That's got cable. Might go with this economy one. Yeah, I'm going to go with this economy one. That's probably close to what I'm going to be getting anyway. Okay, so once we go in here, we get all of these different like specs for the item. But we got this CAD option just here. So all we do is we can download it, and they've got different form factors, right? So do you want a drawing? Do you want a SolidWorks? Do you want... We're going to go for a step file, okay? And we're going to click the download, and as soon as we click the download, it's going to download that file and bring it straight into Fusion. No messing. Might be a slight delay. As it does need to connect to the internet, grab it over, and then visualize the model. All right, so I'm just gonna bring this up here, and I'm just gonna say, there you go, I want you there. And as I said, I don't want the cables. So we're gonna get rid of these cables because they're a pain in the bum. So we're gonna go into the bodies. There's tons of bodies. We're literally just gonna Should I delete the bodies? Yeah. Oh. Okay, we're not going to delete the bodies. Don't think it likes... I'm going to try that once more. Yeah, it doesn't like me deleting the bodies. So I'm going to hide them instead. Awesome. What? Wait, what? The heck happened there? Oh. Why is there so many bodies for this? This is crazy. All right. Okay, so now I've just got the motor, okay? So what we can do is we can say, I'm gonna make a joint. I'm gonna get the center of my motor. I'm gonna align it with the center of my see, that would be how it would be orientated if I had a coupler and we'd have that like hanging off the end of the bench. And that's you're gonna walk into that, right? You're gonna hit your hip. So if I flip it and then let's say move it this way. Something like that, I guess. So then all I would do is I would I'm just thinking a moment. So I would have some sort of mechanism on here to connect these two shafts together. So some sort of pulley system with a GT2 belt. So this faceplate would need to change so that it has the mounting holes for the motor. But we're starting to see the actuator come to shape now. So we're looking at the actuator probably on its side. We would probably mount the actuator like, oh my word. Let's see if we can mock this up a minute. Okay, so that's the sort of thing I'm possibly looking at. And I'm just looking at the interference that this would have. The motor would likely interfere with the carriage. So let's look at this logically, right? We've got the nut on the ball screw. We've got the capture block that the nut screws into, and that will then get bolted to a plate on the side that will form the motion system for the x-axis. So that's going to slide up and down here. And what we don't want is for that to crash into this motor. So if it crashed into this motor, that would be bad. That would be not good. Significantly not good. So I think what the next things I need to do is to model the nut, try and figure out the parameters of the block that captures the nut and the side plate. And then what we'll do is we'll make it travel up and down this actuator, and we'll see what happens when it gets to the motor. But for right now, I think this is a pretty solid start. I mean, let's look at our overall timeline. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we've got 2 more operations than our test ball screw. 2 more operations, and we've got end caps, we've got the ball screw, we've got the C-beam, and we've got a motor for 2 more operations. That is pretty darn slick, if you ask me. I like that. I like that a lot. But this motor arrangement is troubling me. I'm trying to think of a way that I can mount this motor so that it is folded in the way that I show here and does not crash the x-axis traveling up and down the y-axis, and to give as much work area as possible. So I think we've done a decent job in designing this this y-axis. Let's save it there. Now, couple of things we need to talk about is some of the features that this machine is going to have. The machine I've currently got has no end stops, so we definitely want end stops so the machine can automatically home itself. I ideally would like to have a touch plate so that the machine can zero out where the tip of the cutting blade is. A tool changer would be awesome, but that complicates things significantly and will put significant cost onto the budget. I think a tool changer could be possible in the future, considering it would be a spindle swap out. So let me just bring up the Ooze Nest website a second. There's something I did want to talk about in terms of my design choice. So this is a CNC router that we're building, right? It is essentially a 2.5D cutter. It's not necessarily a 3D cutter, and it's only going to have X, Y, and Z axes. I might put a rotary on this, so that's not necessarily the top priority, but I do need to think about that. So this is the machine that Ooze Nest produce, and it demonstrates pretty well. So this has got a router in it, and if any of you have used a router before, then you'll know that they're pretty dang loud. Running a router on these machines is so dang annoying. It's painful, and it's not good for the router to be run for long periods of time. They're not really designed for that use case. So we will be using a spindle. I've got a water-cooled spindle on the CNC machine downstairs. So I've got two choices. We're going to either cannibalize the existing CNC for parts, or we're going to buy a new spindle. And my default sort of thought is I'm going to use what I've already got. And if that works out, then great. But yeah, I've got a water-cooled 2.5 kilowatt spindle with an ER11 collet on it. So that what that means is the bits that I can put in, I've got an interchangeable chuck that I can change the size of the bit that goes in there. So I can run a 1/4 inch bit in there. I can run in a 3.16 millimeter bit for fine work. There's all manner of different things that I can put in this machine. It makes it quite versatile. It is a manual switch over, so I've got to use a series of wrenches to swap things over, but we could in future, you know, decide to put a tool changer on there. That would be slick. That would be really slick, but that's not the goal for this machine that I'm going to be building. Welcome back, Alex. We're just rounding off today's stream. So here's where we got to. I don't know if you saw. We completed the ball screw. The ball screw was completed, I think it was in 4 operations. There are 2 more operations in this design. And I've got end plates and I've got a motor in there, as well as the ball screw with all the geometry that the ball screw has. So at this point, I'm mocking up where I think the motor should go. And I'm trying to problem solve on the fly. As you see with the Zigbee machine, you'll see the motors are hanging off the end of the machine, right? And you know, they look quite, they're pancake motors by the look of them. But the point is that's overhanging my bench. If I walk by this, I'm going to hit my hip on this. And I'm not getting any younger. So, you know, I don't want to smash my hip on a motor. No, it's not going to happen. So what I thought I would do is I would fold the transmission. So I'm trying to figure out where would I place this NEMA 23 motor so that I don't crash any of the moving parts and I don't reduce the work area that I want to be able to use. So that's going to be for another day. But for right now, we've got one Y-axis, I would say 80% complete. That's pretty good. I'd like to see this complete with moving joints at the end of episode 2. So I may well be back tomorrow to complete episode 2. I might make this a daily stream until such time as I get this machine designed. And then we'll go from there. Right then, guys. Thank you so much for hanging out. I appreciate every single one of you. If you found some value in this video, feel free to hit that thumbs up button. If you're not already subscribed to the channel, hit that subscribe button and ring the bell. All the YouTube things, right? I like to scratch build from zero and use open source tools to get me there, or at least free tools. I wouldn't say free. Fusion 360 is open source, but I am using the free version of it. So until next time, have fun, be safe, and make something cool. I'll see you next time. Bye for now.